Millions of miles of fragile fiber optic cables crisscross the ocean floor and run under our streets. This physical infrastructure is constantly shifting. Construction crews accidentally sever cables, server farms lose power. A major news event triggers an unexpected surge in traffic. The physical pathways of the web are incredibly volatile. Look closely at the physical ports on this Cisco Catalyst switch. Data entering here doesn't travel as one continuous stream. It is broken down into tiny, independent packets. At every junction, every piece of hardware has to figure out exactly where to send each packet next to keep it moving towards its destination. There is no central brain telling these packets where to go. Instead, each individual router acts autonomously. They use strict mathematical algorithms to map the available physical connections around them and calculate the fastest way out. A single packet might jump across dozens of routers in milliseconds. The internet stays online purely because these machines can calculate the geometry of their constantly shifting environment faster than it falls apart. To solve this problem, engineers first built protocols based on a method called distance vector routing. In this system, a router only communicates with the hardware it is physically plugged directly into. The math running behind this is the Bellman-Ford equation. A router asks its neighbor, "How many hops does it take you to reach a destination?" It takes that number, adds one for itself, and saves the total. If a neighbor reports a new route with a lower hop count, the router immediately overwrites its local table. It accepts the update completely blind, simply trusting its neighbor's math without knowing the full layout of the wider network. This reliance on local gossip breaks down when a physical connection is severed. When a connection drops, two isolated routers might still think the other has a valid path. They pass outdated routing tables back and forth, endlessly adding +1 to their hop counts. The data enters a loop, bouncing between nodes as the numbers count up to infinity. Depending entirely on neighborhood rumors creates loops and blind spots. As more machines come online, a network requires a clearer view to function reliably. The alternative to local gossip is a system where everyone sees everything. This is called link-state routing, and it forms the basis of protocols like OSPF. Instead of sharing pre-calculated math, a link-state router tests the status of direct physical connections. It then broadcasts that raw status data outward, flooding the entire network with the exact cost and availability of its local links. By collecting these localized updates from every machine, each individual router pieces together an identical, highly detailed map of the complete network topology. With the full map in memory, the router runs Dijkstra's algorithm. This calculation rapidly tests every possible combination to lock onto the single, least-cost route from its starting point to any given destination. Having every router memorize the entire internet creates a massive physical bottleneck. Storing a constantly updating global map quickly exhausts a router's memory, and running complex pathfinding algorithms against millions of nodes crushes its processing power. Total network visibility offers perfect pathfinding accuracy, but scaling that omniscience globally demands more hardware resources than practically exist. To bypass these memory and processing limits, network engineers divide the map. By grouping hardware into hierarchies, a router only needs to memorize details of its local region. Instead of calculating the perfect path to a specific machine across the world, a router calculates the fastest way to pass the packet to the edge of its own cluster, handing it off to the next region. At the highest level of this hierarchy, the regions are known as autonomous systems. These are massive, independent networks controlled by different internet service providers, tech giants, and universities. Connecting these independent corporate empires requires a specialized mechanism called Border Gateway Protocol, or BGP. BGP routers sit at the edges of these networks. When deciding how to hand off data, BGP does not run a strict mathematical calculation for physical distance or network speed. It routes based on complex business agreements, transit costs, and political boundaries. Deep inside the network, routers use algorithms to solve for speed. But at the international borders between autonomous systems, the flow of data is dictated by global diplomacy and trade. The modern internet requires both approaches running simultaneously. Protocols like OSPF find the optimal physical routes across local neighborhoods, while BGP negotiates the handoffs across international borders. Look at the physical interface of this Catalyst 5000 series switch. Behind these ports, silicon processors are continuously running these algorithms against incoming electrical signals. When a fiber line goes dark, algorithms like Bellman-Ford and Dijkstra sense the change, recalculate paths, and reroute millions of packets in milliseconds. The network is a physical infrastructure constantly negotiating its own existence. Through these algorithms, it operates as a decentralized, self-healing organism that ensures data survives the chaos.